So today we start on a new topic, and this is an introduction to digital circuits. I'd like to know, no? Meron na ba kayong background on digital circuits, either from high school or from your lab? Can I just see I don't know, a raise of hands or something? So meron na. What about CML, no? Any background on digital circuits?
Nung nakarang sem lang po nun, yung mga boolean po ba yan?
Yeah, also,
yes,
okay.
sir.
So essentially, a lot of the things that we're going to be discussing might already have been discussed with you, no? But anyway, I'm going to assume here a zero base. Okay. Okay, I just want you to appreciate better why the shift from analog to digital. No? Excuse me. No? And I'm going to do this by illustrating a typical problem encountered. No? So this problem is, I have a dam, no? And I want to monitor the height of the water in the dam from a monitoring station, and that monitoring station is 5 kilometers away. No? Excuse me. No? So the problem is, how can the monitoring station remotely monitor the height of the water at the dam? Now, here's a possible analog solution. And this solution relies on a float. We have a float, and we also have a linear resistor here. Okay. I have a contact here in the middle that splits the resistor into two resistances. No? So this contact splits the resistor into R2 and R1. This is actually what you call a potentiometer. So some of you might have already encountered the term potentiometer in your lab. So this is what you call a potentiometer. Okay. Okay, so if I connect this float to this contact will move with the water height, no? So kung mababa yung tubig, bababa yung contact na yan dito, no? Kung mataas yung tubig, aakyat yung contact na yan dito. Okay. What I want to send to my monitoring station is the voltage across R1. The voltage across R1 by voltage divider is going to be Vs, where this is my supply voltage, multiplied by R1 over R1 plus R2. Okay. Note that R1 over R1 plus R2 will be proportional to the water height. Therefore, I have a voltmeter here. If I have a voltmeter here and that is indicating a voltage, I can recalibrate the voltmeter so that ang binabasa ng tao imbis na voltage is water height. Okay? So that is a possible analog solution. No? Now, before I proceed, may I hear from you, no? What do you think are the weaknesses of this solution? No? Ano lang, no? Kahit na hula lang, no? Albert, what do you think is the weakness of this? Or naintindihan mo ba yung solution? Do you understand the solution?
Yes, sir. Naintindihan naman po.
Can you tell me what you feel might be the weakness of this solution? Either you or Mel? Mel?
Try, sir. It can be inaccurate kasi hindi po siya na yung voltage, yung not the height of the water level is measured, yung voltage lang po, so it can be inaccurate.
Yeah, but if I can recalibrate my voltmeter para height yung sinasabi niya, no? Okay, anyway, no, I just wanted you to think about it, ano? Let me proceed, ano? Ano yung possible weaknesses nitong solution na to, no? I outlined them here, no? First, the accuracy of the reading depends on the stability of the voltage source, no? Yung accuracy ng reading depends on the stability of this voltage. Sabihin natin battery yan, ano? If that's a battery, then the battery voltage will degrade over time, no? So habang naluluma yung baterya, bumababa yung reading ng voltmeter. So hindi na nagiging accurate, no? Let's say this was not a battery, let's say that was a power supply. Ganun pa rin, ano? sometimes meron tayong tinatawag na ripple effect sa power supply or for example, poor regulation sa power supply. Okay, so accuracy depends on the stability of piece of S. The second weak feature, ang haba nitong wire na to, no? Ang haba nitong wire. Remember, I said that this is a monitoring station that is 5 kilometers away. If I am measuring voltage using very, very long wires, nagkakaroon ng voltage drop along my wire. And therefore, hindi na rin uli accurate yung mababasa nito. Okay? Ngayon, sabihin natin, i-compensate natin yung formula, yung voltage divider formula. Let's say we compensate it para it takes into account the resistance of the wire. No? Problema, yung resistance na yon hindi rin yun constant. No? Pag umiinit yung panahon, if this is a wire, pag umiinit yung panahon, tumataas yung resistance. No? Pag malamig yung panahon, bumababa yung resistance. So it's not simple to compensate for wire resistance. Okay. Another bad feature, again, this is very long wire, 5 kilometers long, that can pick up interference. No, there's a lot of interference in our atmosphere. No? Radio wave interference, electromagnetic interference, power line interference. So this can pick up interference. And that interference can affect, again, the reading of my voltmeter. And finally, maybe this might be minor, but itong contact na to also deteriorates. Pag nagde-deteriorate itong contact na to over time, there will be a resistance between that contact and my actual resistor wire. And therefore, magiging mali rin yung reading. So those are the weaknesses of this analog solution. Okay. I'm going to propose an alternative solution. Imbis na magkaroon ako ng resistor rito, I'm just going to have 6 different contacts. No? 1, 2, 3, 4, 5, 6. No? Where the contact is located at particular depths of the water. And so my float now, as it is going up and down, will just make contact with either one of 6 possible contacts here. Tapos ang nakakabit sa float ko is yung power supply, yung positive voltage ng V of S directly. Okay. And now I'm going to have, from these 6 contacts, I'm going to have 6 wires leading to this selector switch. This is now a selector switch. The switch selects one from 6 possible positions. No? And then, of course, the negative of my power supply, that will be connected now to the negative of my voltmeter. Okay, paano malalaman ng operator dito yung depth ng tubig? Ano? How will the operator know what the depth of the water is? Well, dito, he's going to switch to the different locations or to the different wires, no, here, no. And the minute may ma-detect siyang voltage dito, alam na niya from the particular position of the switch which particular contact here the float is making, no. The float is making. And so from that, malalaman na niya yung depth ng tubig. Okay, so the operator at the monitoring station knows the water level from the position of the selector switch, which results in a voltage reading. Okay, okay. Ano yung mga weakness nito? No, again, I just want you to think about it. No, can I hear what do you think are the weaknesses of this solution? Albert.
Siguro,
Try
sir,
lang.
sir, still pa rin po yung sa VS and the long wires.
Yeah, no.
Baka po pa siya.
Well, ganito 'yan, ano. Ngayon, ang pwedeng pwedeng magbago yung VS, pwedeng mahaba pa rin yung long wire. Pero ang ginagawa nito, Tinitignan lang niya kung may nadedetect siyang voltage o wala siyang nadedetect na voltage. Di ba? That's the only thing. So it is no longer sensitive to the value of Vs or the long wire, no? Because when what I want to do here is I just want to detect, uy, meron bang voltage o walang voltage? Did you understand what I'm trying to say?
Yes po, yes po.
So hindi na siya actually sensitive sa VS, hindi na siya sensitive sa mahabang kawad, ano? Okay, ang weaknesses nito, I might as well proceed, ano? Ang weaknesses nito, okay. Well, anyway, sige, features na lang muna, no? So the accuracy of the water level that is indicated only depends on the presence or absence of a voltage. Only depends on the presence or absence of a voltage. It is not sensitive to the variation in the value of Vs. So pag operator ako, no, magsi-switch ako, pag na-detect ko, oh, dito may voltahe, alam ko na, no, which corresponding contact here that is, and then therefore I would know the level of the water. So the water level indication is also not affected by the resistances of the long wire, no? And even if interference is picked up, kahit na may interference na napipick up dito, okay, siguro naman ma-distinguish natin, ano, which one has no voltage and which one has a voltage. No? So the reading is still likely to be interpretable. No? And this solution is actually a crude, I would call it a crude digital system. No? It is a crude digital system. Now, what are the disadvantages? That's what I was trying to ask you to think about. First of all, the resolution, yung tinatawag nating resolution. No? Kasi dito sa solution na to, I can detect supposedly, no, if this was an ideal system, I can detect very small changes in the height of the water, no? Maliit lang na pagbabago sa height ng tubig, magkakaroon na ako ng difference in my voltmeter reading. Samantalang dito, no, malaki yung change sa height ng tubig, hindi pa rin magbabago yung position at which a voltage is detected. So that's what we call resolution, poor resolution. So in this example, only 6 distinct water levels are distinguishable, and each of those water levels will actually be a range of water levels. So that's the first disadvantage. The second disadvantage, ang dami nating wire. Kanina dun sa unang solution, dalawang wire lang, ano? Dalawang wire lang. Dito sa solution na to, napakadaming wire, no? In this particular case, I will have 7 wires traveling from my dam all the way to the monitoring station. No? Ilagay na nating 10 piso isang metro ng wire, no? 10 piso isang metro. So that means that I need 70 pesos per meter. And if I multiply 70 by 5,000, because that is the distance, that is 350,000 pesos in wire. 350,000 pesos in wire, no? The cost of the wire, pwede ka nang bumili ng second-hand na kotse. So that is the second disadvantage. Okay? Yet, if we want to increase the resolution, let's say we wanted it to be more sensitive, kailangan dagdagan natin ng contacts. And if we add contacts, then we would also be adding now wire. No? And therefore, it would even make the cost more. Okay, let me show you another digital solution. This is another digital solution. I'm going to introduce what we call an encoder. No? So here I'm going to have what I call a 6-to-3 encoder, and here I'm going to have what I call a 3-to-6 decoder. Okay. And then now I'm going to have only 4 wires. Earlier I had 7. Now I'm going to have only 4 wires traveling from my dam all the way to the monitoring station. Now, what is the role of the encoder? No? Notice that for the encoder has 6 inputs. At any given time, only one input will have a voltage. No? At any given time, only one input will have a voltage. Kasi itong voltaheng to, itong V of S na to, no? Okay, it will make contact with that particular contact depending on the height of the water, but it will not make contact with 2 contacts, only with 1. So depending on which input has a voltage, ito yung magiging output ng encoder ko. No? My encoder has three outputs. Okay, for every input that has a voltage, there's a particular output combination. And so this is just a sample. No? So for example, if this is the one that has a voltage, ang output ko will be 0 volts, 0 volts, 0 volts. No? Ito naman yung may voltahe, ang output ko will be 0 volts, 0 volts, and V of S. And so forth. Okay. So in effect, I will be able to distinguish, dito I only can distinguish 6, ano? Or I need to distinguish 6. But I will be able to distinguish up to 8 water levels. I will be able to distinguish up to 8 water levels. And if this had been a 4 output encoder, no, kasi right now this is a 3 output encoder. If this had been a 4 output encoder, how many water levels would I have been able to distinguish? Anyone? No? Kung 4 yung output nito, how many water levels will I be able to distinguish? Or how many possible combinations are there? There's going to be 16. Yung ba yung isasagot mo sana, Mel?
Hindi po, papaulit ko lang po sana.
Okay. Okay, so there's going to be 16, no? Okay. And so I'm able now to save on wire, no? I'm able to save on wire. So this is another digital solution. And this is yet another digital solution. This time I'm back to 2 wires, only 2 wires. Pero ang gagawin ko ngayon, I'm going to have what I call a parallel to serial converter. A parallel to serial converter. So ang mangyayari, each input, depending on which input has a voltage, that's going to translate to a sequence of pulses. So now you have to detect sequences, basically, no? Dito you didn't have to detect sequences. But now here, you have to detect sequences. And then that sequence is decoded here in the monitoring station to indicate water level. Okay? So here, I can now have as many contacts as I want, no? What will happen is my sequence will just get longer and longer, but I will be able to work with 2 wires. Okay, so I just wanted to show you this example just to give you an idea why the world shifted to digital. Okay, current day solution, you won't even use wire. So sa ngayon, if you tell me to implement this, hindi ako gagamit ng wire, gagamit ako ng wireless. Bakit, ano? Sabihin natin, 2 wire to, 5 kilometers. So magkano yun? Sabihin natin 10 piso per meter of wire. So that's still how much, no? 10 times 5,000. Yeah, that's right. Sorry, 20 times 5,000. That's still 100,000 pesos worth of. That's still 100,000 pesos worth of wire. Whereas I might be able to buy a transmitter and a receiver for probably less than 1,000 pesos each. that will be able to transmit and receive 5 kilometers. No? So of course, if you can do it more cheaply, that's better. No? And then the other thing is you don't have to lay out the wire. So the layout costs are much cheaper. No? That's why it's cheaper to implement. No? And then you now have modern day depth sensors. No? Yung mga sensor ngayon do not rely anymore on contacts like this, because contacts like this are very easy to deteriorate. No? They use, for example, laser technology or ultrasonic technology or MEMS technology. And then if you take a look at sensors now, pag bumili ka ng sensor, pag minsan yung output ng sensor digital na. For example, I can actually buy off the shelf a temperature sensor, and the output of my temperature sensor will be the temperature already encoded serially. Serial na yung lumalabas na data, no? So that I don't have to have many wires. Okay. So those are current day solutions. Okay, like I said, no, I just wanted to show you this illustration to help you appreciate why we want to do digital instead of analog. Number one, it's cheaper. Number two, it's less susceptible to noise. No, it's less susceptible to power supply, okay, interference, all that. No. Any questions so far? Okay. Okay. So the most common type of digital system, so this is going to be like a review for most of you, is what we call a binary system. Okay. Binary system, you call it binary because each digital element can only have one of two possible values. That's why you call it binary. Now, the smallest unit of information, we call it a binary digit, or what we call a bit. And a bit can have one of two possible states. A bit can have one of two possible states. And we refer to those states as a 1, the state 1, and the state 0. Okay, that corresponds to the value of the bit. No? The bit can either have a value of 0 or a value of 1, and that is the two possible states. And in electronics, 1 and 0 are represented by voltage ranges. So for example, my 1, I can say, okay, any voltage between 4.5 volts and 5 volts, yun ang 1. And any voltage between 0 and 0.5 volts, yun yung 0. So I use voltage ranges to represent 1 or 0. And 1 and 0 can have many possible interpretations. You can interpret 1 and 0 to be on or off. You can interpret it to be active or inactive. Or you can interpret it to be true or false. No? Madami pa yan, no? Asserted, not asserted, blah, blah, blah. No? So madami, no? Many possible interpretations of 1 and 0. Okay, there are basic operations that you can perform on bits. We call this basic binary operations. Okay. Now, these operations can have a single input or they can have multiple inputs. For our single input operation, there's only one possibility, and we call that the NOT operation or the inverter. In the NOT operation, the output is the opposite of the input. In other words, if my input is 1, my output is 0. If my input is 0, my output is 1. Okay, we use this apostrophe sign to indicate the inverter or the NOT operation. No? Sometimes we also use the overscore sign. No? So for example, if let's say A is my binary digit, no? Let's say this is my binary digit. Okay, then not A is A apostrophe. Sandali lang. then this is not A, no? Or A inverted. No? Sometimes we also use this, no? So this is not A, no? So you either use the apostrophe sign or the overscore sign. Okay, for our multiple input binary operation, we have two basic operations. We have what we call the AND operation and the OR operation. And again, no, this is just a review. Your AND operation, the output is 1 if all inputs are 1. Output is 1 if all inputs are 1. Okay, we use the dot. We use the dot as our operator. If we don't put any operator, that is an implied AND. No? So for example, if A and B are my binary digits, A dot B, this corresponds to A and B. No? On the other hand, if I say AB, no, this is an implied A and B. Implied yun, no? Pag walang operator, it's an implied AND. Now, the other basic multiple input binary operation is your OR operation. In your OR operation, the output is 1 if at least one of the inputs is 1. At least one of the inputs is 1. And the operator we use is the plus operator. So if I say A plus B, this is actually A or B. Okay, devices that perform binary operations are called logic gates. So we have, corresponding to the NOT operation, we have the NOT gate or the inverter. Now, how do you describe the operation of a logic gate or logic gates? One way of doing that is through your truth table. So your truth table is a table showing all possible combinations of the input and the corresponding output. So this is the truth table for your NOT. Okay. So if your input is 0, your output is 1. If your input is 1, your output is 0. And this is the circuit symbol for a NOT gate. This is a circuit symbol for a NOT gate. Actually, this is your symbol for this is actually, you encountered this already before, no? This is your symbol for a amplifier. Okay, and then when you see the dot, this is inversion, no? Inversion. So actually, okay, your input goes through an amplifier and then is inverted, no? So ito yun, no? Ito yung inversion. Okay. In other words, if I have something like this, this is also a NOT gate. No? This is also a NOT gate. No? So your output is inverted and then goes through an amplifier. Okay, the reason why you have that amplifier there is because it is impossible to implement the NOT operation without any amplifier element, no? Without any active element. You cannot perform a NOT operation with just passive elements. Kailangan meron kang active element that does some sort of amplification. Okay, any questions before I proceed? Okay. Okay, so what is an AND gate? An AND gate, the output is 1 when all of the inputs are 1. When all of the inputs are 1. No? So this is the truth table for a 2-input AND gate. Okay, so again, what is our truth table? It shows all possible combinations of the input and the corresponding output for each of these combinations. So I have 4 possible input combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And for all of these input combinations, there's going to be only one combination where my output is going to be a 1. Because remember, my output is 1 only when all the inputs are 1. So here, okay, ito na yung implied AND, ano? Wala yung dot operator, implied AND yan. So when you see AB, then that's implied A and B. And this is your AND gate symbol. Okay, this is your OR gate. Ano yung OR gate? The output is 1 when any of the inputs are 1. So of the 4 possible combinations, 3 of those 4, you would have at least one input that is 1. And therefore your output will be 1. So that's your truth table. This is your OR gate symbol. Okay, this is your operator A or B. So those are your 3 basic gates: the NOT, the AND, and the OR. And using those 3 basic gates, you can implement any logic function. No? But I will present some additional important gates. So basically, other gates can be implemented using the basic logic gates. For example, if I stick an inverter to the output of an AND, no? So I cascade an inverter at the output of an AND, what happens is my output becomes A and B inverted, the whole thing inverted. And I now call that a NAND. So ang NAND, actually, this is not AND. No? Not AND is NAND. So this is my NAND gate symbol. Remember what I said about the circle? No? So this indicates inversion. So yun yung sinabi ko din dito sa yan, ano? Inversion. Okay? And then if I cascade an inverter to the output of an OR, that is what I call a NOR. And NOR stands for not OR. And so all I have to do is stick now this circle to the output of my OR, and that is my NOR gate symbol. Any questions? Any questions? Okay, let me test you a little bit, ano? I need a Okay, so try this out, ano? What will happen if I have an OR and then I invert the inputs of my OR? What does this implement? Anyone? Can someone tell me what does this implement?
Not A plus not B po.
Not A plus not B.
Yeah.
Yeah.
A not plus B not.
Yeah, that's right, no? So this is okay. What does the truth table of this look like? No? So let's say this is A, D, B, and this is let's say this is C, no? Which is equal to A naught plus B naught. 0, 0, 0, 1, 1, 0, 1, 1. Ano yung C for the first combination?
1 po.
1. Okay, what about this? The second,
1 po.
1. The third,
1,
and then last.
0.
Okay, so what gate is this? This is actually an AND. So actually, this is also a circuit symbol for the NAND. And in fact, if I get an AND and I invert my inputs, so A prime or B prime, that is A, B inverted. No, this is also a NOR. Okay. This is A or B inverted. Okay, so actually there are many circuit symbols. Basically, what I'm saying is this is the typical NOR circuit symbol. This is the typical NAND circuit symbol. But actually, if you take a look at this is also a NAND, no? And this is also a NOR. Okay. Okay, so gates are usually already packaged in integrated circuits. No? So these are through-hole integrated circuits. These are no longer used in industry or in actual products. Usually these through-hole parts, they're just used by students when they do experimentation. No? Usually your integrated circuits are already what we call surface mount circuits, where the integrated circuit is mounted on a surface and soldered on that particular surface. And these are very, very small. No? These are very, very small. No? These are probably 1/10 or even 1/20th the size of this. Ano? Kasi these are actually resistors. Okay? And the smallest of these resistors, we call this chip resistors or surface mount resistors. The smallest of that, kasing laki na lang bigas, no? A grain of rice. So you can imagine how small this is. No? So for example, for the 7400 IC, okay, you actually have 4 NAND gates inside. No? For the 7402 IC, you actually have 4 NOR gates inside. So pag bumili ako ng IC na ganito na 7400 top view, I can look at it this way, and these are my leads. Here I connect my power supply VCC. Here I connect my ground, no? And then here I can pick any NAND gate. These are my inputs, and this will be my output. No? So the same with my 7402, and then in my 7404, I actually have 6 inverters inside. So I just connect this to my power supply, this to my ground, and then my input will be any one of the inverters, and I pick out my output from that particular inverter. And in these gates, these are what we call TTL gates. No? It's a very old. This is a very old technology for implementing integrated circuits, which we call transistor logic. Your 0 is anywhere from 0 to 0.8 volts. And your 1 is anywhere from 1.5 to 5 volts. No? In other words, these are as inputs. No? If I input anywhere from 0 to 0.8 volts, that would be recognized by this particular gate, for example, as a 0. And if I input anywhere from 1.5 to 5 volts, that would be recognized by the same gate as a 1. No? Okay, and my output typically for TTL, zero output, I think is less than 0.5 volts, and a 1 output is, I think, about 4 volts or something like that. No, I can't recall anymore. But anyway, yeah, no, those are integrated circuits where you have gates. This is the ideal transfer characteristic of an, or this is the transfer characteristic of an ideal inverter. So this is my inverter. No? Of course, I have to have a power supply connection and a negative power supply connection or a ground connection. So kagaya dito, no? May power supply, merong ground. Okay. This is recognized as, okay, so this is my input, this is my input, and this is my output. No? So this is recognized as the range of my zero input. So this is my zero input. And this is recognized as my one input. Okay. And Vref is the threshold. No? Vref is the threshold. In other words, my zero input is anything less than Vref, and my one input is anything greater than Vref. And whenever my input is zero in an ideal inverter, my output will be what we call V's of H. No? V's of H. That is the nominal voltage corresponding to a high logic state, no? At the output for my input being zero. And when my input is a 1, my output will be V's of L. The nominal voltage corresponding to a low logic state. No? When my input is high. No? When my input is high. So this is the ideal characteristic, the transfer characteristic of an ideal inverter. Unfortunately, we do not live in an ideal world. And this is how a real inverter's transfer characteristic will look like. I don't know if you will recognize this, but this is actually the transfer characteristic of a MOS transistor amplifier, or a BJT amplifier. Now, except that in the MOS or in the BJT, we use it in the linear region, no? Or we use it rather in the active region. No? So if this is a BJT, ito yung active region. No? So this is the active region if BJT, and this is the saturated region if MOS. No? Ito yan, no? From here to here. On the other hand, ito naman, okay, this is the cutoff if BJT, or cutoff if MOS. And then here, okay, here, okay, this is saturated if BJT, or this is linear region if MOS. So this is actually the transfer characteristic of a common emitter transistor circuit or a common source NMOS circuit. And then I'm showing you the different operating regions. Now, if this is used in digital, we don't use this portion. We don't use this portion in the middle. No? We only use it when it is cut off, or when it is either saturated if transistor or linear if MOS. No? So dito lang natin ginagamit dito sa area to and dito sa area to. No? So this middle portion, this is what we call the undefined logic state, because actually it's not used for logic circuits. Now you have your input here and you have your output here. Okay. My input, my one input can be anywhere from VIH all the way to V plus. Now, in other words, anywhere from here, VIH, anywhere from this value, VIH, to V plus, that would be recognized as a 1. But my output, no, so this is my input, no, from anywhere from here to here, that's recognized as a 1. But my output, no, will be a 0, no, will be a 0. Kasi kung 1 yung input, my output will be a 0. That output, the maximum value will be this, no? Sorry. The maximum value of that output will be this, VOH, no? That corresponds to when my input is its minimum. Okay. Of course, the minimum value of my output will be wherever this line ends. Okay. But that is this range. Ito yung range na to, no? In other words, when this is my input, ito yung magiging output ko. Okay. Ganun din dito, no? When this is my input, my 0, this is going to be my output. When my input is VIL, VIL is the maximum possible low input voltage. So, saan yan dito, no? VIL here, no? That's the maximum possible low input voltage, which will be interpreted as a low. My output will be VOH, no? So ito, when this is my input, this is my output, VOH. Okay? So that's why this range corresponds to this range, input and output. Okay, this is what I call my noise margin. No? NM, this is my noise margin. Okay, why is that called your noise margin? No? Because, okay, this is what my output, this is what is output, ano? Itong range na to. But hanggang dito, it is still accepted as a 1. Right? This is still accepted all the way down here as a 1, and this is what it will output as a 1. And therefore, if there is some noise that reduces my output by this amount, it will still be accepted as a 1. And that's why you call it your noise margin. So you have your noise margin for your high, and you have your noise margin for your low. That is the characteristic of a real inverter. Okay. Are there any questions? Maybe you have to take a look at this again, ano? Because looking at it, it looks intimidating. But go through my explanation and then go through the descriptions of the different voltages, and then eventually you'll understand it, ano? Okay. Now there are many different ways of implementing logic circuits. We're going to introduce you to 3 here. So this is going to build upon what you already learned about diodes, about BJTs, and about NMOS. No? So we have what we call diode logic. This just uses purely diodes. We have resistor-transistor logic, which uses transistors and resistors combined. And we have what we call NMOS logic, which uses MOS transistors and resistors combined. So those are the 3 that we're going to introduce in this course. Actually, it's not going to be introduced in this course, but the most common logic implementation now is what we call CMOS logic. No? CMOS logic. And CMOS stands for complementary. Yeah, this stands for complementary MOS. No? Complementary MOS. In other words, your logic gate is a combination of NMOS and PMOS transistors with no resistors. So hindi natin pag-aaralan to, no? But I thought I'd mention it anyway because that's actually the most common logic implementation nowadays. Okay, diode logic. Okay, one of the disadvantages, by the way, of diode logic is you cannot implement the NOT gate. It's not possible to implement an inverter. You can only implement an AND and an OR. And therefore, diode logic by itself is not a complete logic family. Because a complete logic family, you should be able to implement all possible logic functions. Anyway, diode logic. This is the implementation of a 2-input OR gate. Okay, if we analyze this two-input OR gate, no, this time we feed into the truth table the possible combinations of input voltages. So ang ipapasok natin ngayon dito, imbis na 1 or 0, yung mga input voltages. So let's say my input voltages, my 1, so this is my input voltages. Okay, my 1 is 5 volts and my 0 is 0 volts. If we were to use the ideal diode model, then this is going to be my output. This is going to be my output. But the ideal model is not, how do you say it? No? The ideal model is poor to use in logic circuits. The reason for that being, the voltage drop across your diode is comparable to the voltages that you apply in your circuit. No? Sabi natin when we introduced diodes before, that you only use the ideal diode model when the voltage drop across your diode is insignificant compared to your other voltages. But in this case, kung silicon, 0.7 is not insignificant compared to 5. So actually, what you normally use is the constant voltage model. Okay. So in the constant voltage drop model, okay, when both my inputs are 0, my output is 0. But when any of my inputs is 5 volts, my output will be 4.3 volts. And that's very easy to see. No? So for example, let's take this as an example. No? Let's take this as an example. So let's say A is 0 volts and B is 5 volts. No? So if A is 0 volts, let's say this is A, that means this is grounded. And then B being 5 volts, that means I have a 5 volt supply here. And then this is my output, which is Z in this case, no? Z. Okay, what are the states of my diode going to be? No? What are the states of my diode going to be? The voltage at Z is either going to be 0 or positive. The voltage at Z is either going to be 0 or positive, which means that this diode will never be conducting. Because for this diode to conduct, the open circuit voltage across this diode's terminal should be greater than 0.7. So this will never conduct. Okay, on the other hand, if I take a look at this loop, notice that my current is tending to flow in the clockwise direction. No? So that's already an indication that maybe this is conducting. Now, how do I know that this is conducting? Now, again, there are two techniques. One is to assume it's conducting, replace it with its equivalent circuit. The other is to assume it's not conducting, replace it with its equivalent circuit. If I assume it is not conducting, no, so assume, so this is D1, ano? D2. D2 is not conducting. Okay. So ito, alam na natin that this is open circuit, no? So we can disregard that. So what will my circuit be now? So this is B. Okay. This is Z. This is R. What will be my open circuit voltage across D2? So V sub D2. V sub D2 will be equal to 5 volts. So this is greater than 0.7 volts. And therefore, my assumption is wrong. No? Assumption is wrong. This assumption is wrong. And my equivalent circuit will now be, I have 5 volts here. I now have 0.7 volts here. And this will be R, and this will be Z. And obviously Z, or V sub Z, will be equal to 5 minus 0.7, which is equal to 4.3 volts. So yun yung sinasabi natin dito. And that will happen in any of these 3 cases. Okay. Now, why do we say that this does not scale? No? Why do we say that does not scale? No? That's because, okay, for example, what will happen if I have okay. So let's say this is 5 volts, this is 5 volts. Okay, this is 5 volts, this is 5 volts. Oh, sorry. No, wrong. That's not what I want to do. Sorry. So this is 0 volts, this is 0 volts. And this is 0 volts. No? Why do we say this does not scale? No? Okay, eventually, okay, ang magiging output voltage natin dito, as we showed, is 4.3. No? Okay, if I have 4.3 volts in one input and 0 volts in the other input, ito mababawasan uli ng 0.7. So this is going to be what? No? This is going to be 4.3 minus 0.7. This is 3.6. And eventually, ito mababawasan uli ng 0.7. This is going to be 2.9 volts. So pababa ng pababa yung voltage. No? Pababa ng pababa. Each time it passes through an OR gate, a diode OR gate, your voltage goes down by 0.7. Okay? So the voltage will continuously go down until it is no longer recognized as a 1. At some point, the voltage will be so low that it will no longer be recognized as a 1. It will already be recognized as a 0. And that's the reason why we say this does not scale. Okay. And that does not happen with resistor transistor logic, and that does not happen with NMOS logic. So that's your OR gate, no? Now the AND gate, okay, this is your diode logic AND gate, 2-input AND gate. Again, it is inappropriate to use the ideal diode model, no, because your diode voltage is comparable to your input voltages. So what you should use is the constant voltage drop model. No? Okay. When both inputs are 1, that is, both inputs are 5 volts. Okay. Notice that you have 5 volts here, you have 5 volts here. So the open circuit voltage across this diode is going to be 0. That is not enough to make it conduct because you need 0.7 volts to make this conduct. So this is going to be an open circuit. No? And then you have 5 volts here, 5 volts here at this point. I'm talking about this combination, dito. Then also the open circuit voltage across this is going to be 0. So this is going to be an open circuit. And therefore, if both these diodes are open circuit, then what is the value of V sub Z? That's just equal to 5 volts, no? Assuming that this is not drawing any current. So that's going to be equal to 5 volts. That's why you have this combination here. Now, what happens when any of this become 1? No? So pag 1 yung isa dyan, so this is 3, this is plus 5. Okay. So let's say itong kombinasyon na to, no? Or itong kombinasyon na to, 5 and 0, no? So let's say this is 5. And then here, my second diode, this is 0, no? 0 volts. What is my Z? So again, this is 5 volts. This point is 5 volts. So this will not have an open circuit voltage greater than 0.7. So this will be open. On the other hand, this is 5 volts. This is 0. The open circuit voltage across this will be greater than 0.7. So what is my equivalent circuit? I have 5 volts R. This is now going to be equal to 0.7 volts ground. So VZ is just 0.7 volts. So ito yun, no? Any of these combinations will result in 0.7 volt output. Okay, and this has the same problem of not being scalable, no? Because okay, this is supposed to be a 0. 0.7 is supposed to be equivalent to a 0. Okay, every time you cascade AND gates together, una yung 0 is 0, tapos magiging 0.7, and then madadagdagan ng 0.7, magiging 1.4. Eventually, no, if you have AND gates cascaded together, okay, so let's say this is 0 volts, this is 5 volts, this is 5 volts, and this is 5 volts. Ang output mo rito will be 0.7 volts. No? Dito, ang output mo, your input is 0.7. So imbis na 0 rito, meron na akong 0.7. And then add this 0.7, this is going to be now 1.4 volts. And then this is now going to be another 0.7, 2.1 volts. So the output increases to the point it may no longer be recognized as a zero. Kasi palaki ng palaki, no? To the point where it may longer be recognized as a zero. Okay, so that is the problem with diode logic. Okay, I'm going to ask you to just do this on your own. So 2 parts to this example. First part is construct the, so 2 parts. So first, you show the circuit. And then second, okay, show the truth table in terms of voltages. So instead of ones and zeros, I want you to show the truth table in terms of voltages, no? Where initially you can assume that 0 is 0 volts and the 1 is 5 volts. So pakita nyo kung anong lalabas na voltages dito for these different input combinations. So please try that on your own, no, as an exercise. So I'm going to stop there. Next time, we're going to study now RTL. So this is resistor transistor logic. So how to implement inverters, NOR gates, NAND gates. And then we're going to take up MOS logic, NMOS logic. So inverter, NOR gate, and NAND gate. No? So that's it. No? That's all I want to cover for today. Are there any questions? Any questions? Okay. Yeah, that's it. So I'll end the recording now.